These are very trying times for us in cosmology, my friends. But first, this is what Professor Kaku had to say to us a year ago.
Hey, Professor, say the universe is about 13 billion years old. What if it's not?
Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. Now, it takes many billions of years to create a galaxy, like the Milky Way galaxy, with 100 billion stars, many billions of years old. But the James Webb Telescope has identified 6 galaxies that exist half a billion years after the Big Bang that are up to 10 times bigger than the Milky Way galaxy. That shouldn't happen. There should not be primordial galaxies that are bigger than the Milky Way galaxy that are only half a billion years old. Something is wrong.
Firstly, I'd like to proceed by saying I love you all, and I am sincerely grateful for your immense support on this channel. Kindly tell us what country or state you are watching from in the comments. But today's episode kind of has a little twist. With the James Webb Space Telescope pushing the boundaries of what we can see, astronomers are currently enjoying a productive period of discovery more than 2 years after its successful launch. For cosmologists, nevertheless, the discoveries have also unlocked a Pandora's box of mysteries. Astronomers are now gazing at a galaxy that may be among the oldest ever, and the startling thing is that it already contains billions of stars. The telescope's observations recently entered the first 500 million years after the Big Bang, and this time it saw galaxies that are most definitely anything but infantile, in that they are extremely massive and mature than previously expected for such early times. Notably, this cosmic monster was discovered by the Hubble Space Telescope as an odd point of light in its area of view just 2 years ago. Until they turned Webb to look at it, scientists could not have realized that this strange pinpoint of light is a hideous galaxy looming at the brink of time. Webb's discovery showed that the point of light is in fact a primordial galaxy that is significantly larger and more developed than it should be. Known by its redshift of Z equals 9.3, this galaxy, GZ9P3, was formed just 510 million years after the Big Bang. Other galaxies have since been observed between 300 and 500 million years after the Big Bang, but none of them is as large as this one. These results taken together suggest that the galaxy's current size was achieved by stars within it, forming more quickly and successfully than was previously thought. GZ9P3 also has a strange shape that could reveal secrets about the early universe. The people who made the finding saw that the galaxy has 2 bright spots inside it that show its 2 dense centers. This definitely points to a galactic merger, which would mean that 2 very early galaxies crashed into each other in the beginning of the universe. The team also found out how old this galaxy is, how much it weighs, and what shape it has. They also looked closely at its stars and saw that most of them are young, bright ones. They used the JWST to look for certain elements in the older stars of GZ9P3, such as silicon, carbon, and iron. The strongest thing that stars can make is iron. When these stars blew up, they sent these elements into space, adding metals to the early universe that later became part of new stars. They also learned that GZ9P3 had more old stars than they thought. This means that galaxies may have chemically matured faster than we thought. This could be because stars added metals to the universe faster than we thought. The unexpectedly mature older population of stars in GZ9P3 questions what we think we know. It suggests that stars formed much earlier than we thought they would have to have aged enough by this point in time. These results suggest that we might need a new model to explain how galaxies grow so quickly and become so chemically mature, as well as how they get so big. They also suggest that galaxy collisions may have been the main thing going on in the universe right after the Big Bang. Our current understanding of the universe might not be wrong, but our ideas about how quickly galaxies form probably need to be changed, since these galaxies are much bigger than we thought was possible.
Astronomers in Durham have made the biggest ever computer model of the evolution of the universe from the Big Bang to the present day using one of the most powerful supercomputers in the world. The model was based on the accepted theories of physics, but when it was compared to how the universe actually looks, there were significant differences. So, was Einstein wrong after all?
Despite constructing our cosmological model using observations, theories, and mathematical support, there are some indications that the universe is not entirely aligning. Perhaps you're familiar with the current crisis in cosmology. Essentially, the crisis began when various techniques for determining the age of the universe began yielding conflicting results, which continue to perplex cosmologists. The James Webb Space Telescope, with its recent discoveries, has further exacerbated the crisis. As we observe the vast expanse of the universe, we can see that galaxies are continuously moving away from us, indicating the expansion of the cosmos. When we calculate the rate of the expansion of the universe using the cosmic microwave background, which is the light remaining from when the universe was only 380,000 years old, this is the result obtained. Then, there's another approach where we can determine the expected brightness of distant supernovas and compare it to their measured brightness. By utilizing that data, we can make an estimation of the rate at which the universe was expanding during the occurrence of the supernova. When we calculate the expansion rate using this method, which is commonly referred to as standard candles, this is the result we obtain. The Hubble constant is the term used to describe the rate at which the universe is expanding. Nevertheless, the disparity between the outcomes of the two approaches is referred to as the Hubble tension. This, my friends, is the crisis in cosmology. However, this is no longer the sole crisis at hand. A recent cosmological dilemma has arisen, posing unprecedented challenges to our models.
I've spent all my life developing a particular theory of the universe, and now that theory is being questioned. I welcome that, because that's how we move forward. That's how we make progress in science.
If you are not in a city or anywhere else that blocks starlight, there are a gazillion stars visible when you look up in the sky. One of the smudges among the countless stars is the Andromeda Galaxy. That is so because galaxies and stars abound throughout the universe. How much of the cosmos do they fill is the question. Stated otherwise, how much matter is there really? An easy inquiry with a far from straightforward response. The main reason of this conundrum is that modern cosmological observations just cannot agree on the distribution of stuff in the cosmos. And this has resulted in the enigmatic S8 tension, sometimes known as the new cosmic crisis. Currently, the lumpiness or clustering of matter in the cosmos is measured by the S8 tension. Said another way, consider the cosmos as a massive jigsaw with its parts dispersed over space. The distribution and clumps together of this material are interests of scientists. Measurement can be done in two ways. First, by using low redshift measurements like weak gravitational lensing to calculate it correctly. Gravitational lensing is a phenomena in which the enormous gravitational attraction of massive objects, such as galaxies and black holes, bends and distorts light from farther off objects that would otherwise be invisible, offering new perspectives on the cosmos. The S8 value, however, acquired from the second approach, the conventional cosmology model, based on measurements of the cosmic microwave background, does not agree with values found in low redshift observations. The confusing core of the S8 tension is formed by this disparity. What now is to be done? We obviously do not fully comprehend some things. Something that, for all the ideas and observations and fictitious entities that back them, doesn't quite add together just what is happening. To discover out, scientists ran the biggest cosmological simulations ever on one of the world's most potent supercomputers. It is impossible to really appreciate the scope of this effort unless one considers that the simulations needed almost 50 million hours of computer time spread among the 30,000 processors that comprise Durham University's Dirac Cosmo 8 supercomputer. FLAMINGO, a long acronym for Full Hydro Large Scale Structure Simulations, is the project that uses entire sky mapping to explain future generation observations. FLAMINGO differs from past simulations not only in size and resolution, but also in the incorporation of much more than gravity. As dark matter is the primary component of matter, most cosmological computer simulations of our universe have up until now concentrated on modeling it alone. Nevertheless, even though typical baryonic matter accounts for only 1/5 of all the mass in the universe, it can significantly influence the distribution of cosmic matter at close range. Galaxies' expansion may be halted, for example, by galactic winds driven by supermassive black holes and supernova explosions. FLAMINGO also tracks and considers ordinary matter, unlike earlier simulations that simply took dark matter into account, since, while dark matter still dominates gravity, the contribution of conventional matter cannot be ignored. Though it made great strides, such as precisely replicating the birth of the Milky Way and Andromeda Galaxy, among many other things, the simulation was unable to explain the observed weak clumping of matter in the modern universe. Stated differently, the S8 tension, exactly what it was designed to aid with, was not resolved. Alternatively, should I suggest that our beloved mainstream model of cosmology may be seriously flawed? The simulation also runs counter to the distribution of matter in the cosmos as reported by the James Webb Space Telescope and other observatories.
The current theory beautifully explains how galaxies evolved, but there's a problem. It predicts that they're 7% more closely clustered together than they actually are. The new computer simulation is much more detailed, and it takes into account the role of supermassive black holes, but that's not right either. It's still 5% more clumpy. So if the best computer simulation ever created can't get the right result, there are two possibilities. Either the measurements from the telescope is wrong, or the cherished theories of physics might be incorrect.
Recent observations from Webb has proved that the Hubble tension actually exists. That's right, the James Webb Space Telescope has cross-verified the findings of its predecessor, the Hubble Space Telescope. The pioneering observatory discovered that Hubble's calculations of the universe's expansion rate are exceptional, intensifying the so-called Hubble tension. In essence, measurements of the universe's expansion rate defined by the Hubble constant simply do not align. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. With measurement errors ruled out, what remains is the intriguing and exhilarating possibility that we have misconceived the nature of the universe. New theories are already making its way into the limelight, with some calling for the removal of dark matter. There is a major shift about to come, and it is already on the horizon. That's what I feel. What do you think? Drop in your comments below. Also, channel membership is now live. Please help me buy a cup of coffee if you enjoy my content. Until next time,